Hello everyone, my name is Romain. I'm a researcher at the University of the ETH Zurich in Switzerland, and today I'm going to talk about why the internet is getting emptier and why this is a sustainability problem. You may wonder what consumes more energy in today's ICT ecosystem, data centers or telecommunication networks? Well, it's a tricky question, and the best numbers we have to answer them are showing that so far the orders of magnitude are kind of comparable, between 2 to 300 terawatt hour per year. If we take a step back in time, in 2015, the estimates were already kind of in the same ballpark for the two systems. The numbers have grown all the time, a little bit, but in similar proportion. Interestingly, in the same time interval, the amount of useful work done by either systems has increased a lot more than the energy. That tells us two interesting things. The first is that the energy efficiency of both systems have improved a lot because we are able to do a lot more useful work with a comparatively small increase in energy. But of course, that increase in energy is still positive. So that means the improvement in efficiency hasn't been enough to compensate the growth of the infrastructure. And that is a problem because it is fairly easy to keep building new data centers or to keep growing the internet infrastructure, but it's going to be increasingly harder to keep increasing the energy efficiency. On the other hand, electricity production today is still primarily dominated by carbon-intensive sources, so requiring more electricity is a rather bad sign. And if we look at the total volume, the electricity productions has doubled in the last 30-something years. Right? So we are effectively demanding more and more, and still a very large share of this comes from carbon-intensive sources. So that growth is a problem. And if we look at the internet more specifically, we should not forget that internet access is still today far from being universal. Today, only slightly more than 60% of the world population is estimated to be having access to the internet. So the growth is expected to keep being there. Now, let's zoom in. I talked about the ICT system in general, data centers, telco, but what's even the internet? What is it that we're talking about? Well, the internet is a network of networks. Here's one of the most famous depictions of what the internet is. So what you can see on this image are many bubbles. Each bubble is one network. And the line in between those bubbles are the links that connect the different nodes in those networks, nodes that we call routers. And the lines in between those bubbles are the interconnection between the networks. And this is why the internet is a network of networks. Now, let's zoom in. Here's one of such bubbles. It's a middle-sized network from Switzerland, which is called Switch. Here is the map of this network. So each of those dots is one router, and the line represents the links in between the routers. Here is what the average link utilization in that network looks like. We can see patterns that are pretty intuitive. We have peaks during the daytime where people work, and we have valleys during the night. And at the beginning of this graph, you see a weekend day where, well, there is no peak because people don't go to work, usually. Now, what do you think is the average link load in the switch network? 2.1%. I'm pretty sure you had a larger number in mind. How can that be? And obviously, the first question you ask yourself when I present such a number will be, how general is this? Well, I cannot tell you this because internet service providers, so the people that operate those networks, they don't like sharing those numbers too much. But we've got access to a couple of them, and they are all in the single-digit numbers for the smaller networks. So I cannot generalize, and for sure some networks have larger average utilizations, but what I can say for sure is that single-digit numbers are not rare. On the other hand, the total volume on the internet is increasing. You can see here on this graph the normalized traffic volume of Telefonica and Cogent, that are two of the largest networks we have in the internet. and they have a pretty clear and strong increase of traffic over time, while the energy remains reasonably constant. The important thing is this increase is not constant over the time of the day. So what this plot here is a bit difficult to apprehend, but what this plot is trying to show is that each data point quantifies the delta between the maximum amount of power of traffic and the minimum amount of traffic we send for each hour of the day. Of course, it varies over the time of the day, but what's important is that series of line that shows passing of time, year after year, the line gets higher. That means that as we go on, the difference between the max amount of traffic and the mean amount of traffic grows. Let me try to illustrate what that means in a picture. If we say that a network, the internet, is a network of roads, right? We have time of the day where the networks are rather empty and there are times where they're full. As time passes, we are building more and more of such roads, and similarly, those roads are sometimes empty, sometimes full. So the difference in terms of number, absolute number between empty and full is growing over time. And as a consequence, the network are getting emptier on average. Why does it matter? 20 plus years ago, some researchers made the somewhat interesting and provocative claim that the core of the internet, so those routers, consume more energy per byte that they transmit than if we were using wireless LAN to do this. Actually, quite a lot more energy, depending on the assumption you make on how the wireless connection will look like. How can this be? How can this be true? Well, there are three factors that explain this. The first is that in the internet, when a router is being deployed, it is being connected and it remains on, always. You don't turn it off when you leave the room like you would do for the light. The second thing is the network device's energy consumption is reasonably independent of the load. That means the power cost that you pay when you plug in the device is very high in comparison with the increase in power when you start sending more and more traffic up to a utilization of 100%. Let me try to illustrate what that means. That means that the internet is actually not really a network of roads. Why? Because if you think about a road, when the road is unused, the road does not consume any energy. The internet is more like Hyperloop tubes, where the Hyperloop needs to spend a lot of power to create a vacuum in that tube, so that that needs to be there all the time, whether you have a train passing by the tube or not. So that's what it means, that the energy consumption is independent of the load. And the third factor is what we already saw. Networks tend to be underutilized. Right? And this is for sensible reasons. This is because the people that manage the networks, they over-provision intentionally so that they can provision for the peak, right? They can make sure that they have enough capacity when we have that peak that we saw in the plot before. And in case things fail, then traffic will have to be rerouted and so on. But the consequence of when you compound those three things is that we operate most of the infrastructure in the least efficient operating point, right? We get the red curve and we use it at the time where we pay most of the power for the least usage, whereas what we want is something that is a lot more proportional. So if you think about this, there are two ways that you could improve the energy efficiency. The first is, well, try to push it towards higher utilization, and then you amortize the idle cost more. Or you could try to take the low power utilization lower down. Right? This is what I'm going to talk about in a little bit more details. So the basic idea to do this, to lower this bar, is to turn things off when you don't need them. Right? So the type of things the system we're talking about I show here on the slide, that's a router. Right? Functionally, it's kind of the same box that you have at home that gives you internet. It's just a bigger box that functionally does the same. It has ports, like those black holes that you see, and in each of those holes you can plug a transceiver, which again is comparable to an RG45 cable or what you know as an internet cable, just bigger. And so in such a system, you can turn off one port, you can turn off a line card, which is effectively a set of ports, or maybe the entire router. But also you could imagine turning things off that are inside the router, like some memory banks you don't need, or some redundant power supplies, and so on and so forth. And it's not really the purpose of that talk, but it's not black or white, right? It's not on or off. It can be more subtle than this. But functionally, it's fairly simple. It's a simple idea, and it's an old idea. We know this for a while, that we should turn things off when we don't need them. In fact, academics have proposed a long time ago such ideas of how to do this. And what they show is that if we have networks with an average utilization that is fairly low, which, as we saw in the introduction, is fairly common, then we could expect energy saving that are in 50+%, very, very high energy saving numbers. How they do this, essentially, the idea is that you could buffer the traffic at the entrance of your network, right? So you make the traffic wait while everything is asleep, and then so you buffer for some time, and then you wake everything up, and then you send all the traffic in one go as what they call a burst. And if you do this in a smart way, then you can make sure that you don't impose too much delay on the traffic. And this is how you get so much savings. But it's making an important assumption, which is that we should be able to wake up the link in 1 millisecond, or they study other values, but in the millisecond range. And so we thought, how are we today? How far are we from this today? Can we effectively do this? So we started measuring, and we found that to effectively wake up something, the values are not in milliseconds, they are in seconds. Okay. So we have hardware that is effectively 1,000 times too slow to do this buffer and burst. So we can't do it. But maybe we can still sleep if we consider longer timescales. I showed this graph before. We have very strong and very stable patterns between day and night, for example. So it doesn't seem impossible to say at night we're going to turn off some links because we don't need so much capacity, and we're going to turn them back up during the day. And if you do that twice a day, waiting a couple of seconds sounds acceptable. It's functionally not very different from other network management tasks that are being performed routinely. Okay, fast forward 6 months, we've done this. We created a protocol we call Hypnos that effectively implement this. And on the switch network, we find that we can turn off about 1/3 of the links. In the presentation, you have the links to check this out if you want to know more. But the key question is, how much does it save? Well, again, fast forward a few months, we've learned that it would actually save very little, almost nothing. So we can turn off 1/3 of the links, but we save nothing? How can that be? It's a complicated question, but a big part of the answer is that when you turn things off, it does not mean you power them off. And that's something we've learned very recently. So let me try to illustrate what it means. It means that if you take this router and those transceivers I showed before, the router alone, so empty, draws roughly 100 watts. Right? And those transceivers, they draws about 3 to 4 watts per transceiver. So there are 32 ports on that router. If you have 32 times 4 watts, you can make the math. You see the cost of the transceiver is about the same order of the cost of the router. So if you turn off 1/3 of them, you would expect that you save something. Except that this power cost you pay as soon as you plug the transceiver in, regardless of whether the port is up or down. What it means is that unless someone comes to the router and physically unplug the things, you won't save anything. And we saw other examples of this. For example, on Juniper devices, there are some series of routers where some other components remain on all the time, regardless of whether the ports are on and off inside the router. And that's just a bug. That's something that thankfully they're starting to notice and that they can fix. Right? And they say, oh, there is this special and normally not used configuration keyword that will effectively turn power off this stuff. We can do it. It's a bug, it can be fixed, and it must be fixed. Finally, the last point I want to discuss in this presentation is that I would argue, and that may be more controversial, that we must keep the internet empty. Why? Why am I saying this? I've shown before that we have a link utilization that is fairly small. I showed the numbers in percentages. If to convert this to the total amount of traffic, it's about 1 to 2 terabits per second worth of traffic for the entire switch network. Now, if you count the energy that is required just for sending this traffic, right? So everything is on, the links are up, and so on. And just to the extra cost to send this traffic, 1 to 2 terabits per second, the ballpark number is 6 watts. That's 0.02% of the total network power. It's nothing. It's noise. It's not there. So once one makes this observation, it sounds like a pretty good idea to go, on the right side of that plot to say, like, we want to run at high utilization. And I argue the opposite. I argue that this is only a good idea in the short term. Why? Because don't forget that the ISP over-provisions the network on purpose. That means that if you increase the demand, so you push the capacity closer to 1, even very far from 1, but you increase the demand, that will trigger in response a growth of the infrastructure. And then we're going to say, again, following the same logic, oh, but we have so much capacity and now this capacity is unused and so it's so inefficient, we should use more of the capacity. And so we're going to create more services that consume more bandwidth. And again, that will increase the demand and the demand will drive infrastructure growth. And ta-da, we have a feedback loop that stimulates a continuous growth of the network infrastructure. And the issue here is that even though the direct cost of the traffic is negligible, the cost of building new routers and deploying them and operating them is far from negligible. And every time you deploy a new router, you have 300-400 watts worth of power demand. And this is what this plot on the right is trying to show. So the bottom line is, as we keep asking for more resources, more from the network, the energy use will keep rising. Pretending otherwise is just a lie. So I think it's very important that we embrace digital sobriety. We need to be aware that everything we do has a cost. Everything we do on the internet has a cost. The individual cost of just uploading a picture or sending an email, watching a movie might be small, but it has a systemic effect, and that systemic effect is not small. So be mindful of not using resources you don't need. Another point I want to make is that sobriety does not mean that, or does not necessarily imply worse user experience. Right? There are some huge software bloat that can be fixed, right? That would allow to deliver the exact same service with a much less demand from the network. But more fundamentally, today the application we use would suffer from a bad network or a slow network or an intermittent network because they were designed under the assumption that the internet connectivity is there all the time and fast. It doesn't have to be. Applications, services can be designed in a different way to provide great experience while performing on a network which is not up 100% of the time and super fast. Oh yeah. So I mentioned that I would talk about the zoo in my presentation. So what's about the zoo? I alluded to the fact in my presentation earlier that it's pretty hard to know how much power a router draws. And this is because the vendors of those routers, they don't provide really any useful info for this. They provide some info about the power, but it's more for sizing the total need rather than to know how much it would draw in practice. In those routers, you have sensors that should in theory tell you, how much power is being delivered, but we found out that not all are trustworthy. And more fundamentally, there is no standard of what should be measured and how it should be reported, which makes aggregated data to get a global picture extremely hard. So we need more efforts, more power measurement being done, and more systemization on what to measure and how to report it. And for that, we created a public database that we call the Network Power Zoo, which is a pun to an older networking dataset. that is meant to become the home of a lot of various type of power related information for network devices. So if you happen to have or operate a network that on which you monitor power data, let us know. It will be very interesting to incorporate this data into the power view. So to wrap up, today I first explained that yes, the internet peak traffic increases and the total traffic increases, but only the peak. And the peak is driving the network growth, which results in emptier network on average. That matters a lot, in fact, because the hardware we have today is very inefficient. It's very far from proportional, and that means that we operate the network most of the time in its least efficient condition possible. That's something that can be improved and absolutely must be done. Finally, I've argued that it's not because the direct cost of traffic is minuscule, and it is minuscule, that sending traffic doesn't matter. It does. It has a very important systemic cost, which is the growth of the network infrastructure, which is the first point of view. So please bear in mind that you should not send traffic that you don't need, and you should be mindful of sending just what you need. Be sober in your demand of resources. And more importantly, if you can, try to stay away from the peak, because ultimately this is what really drives the growth of the infrastructure, and so the total footprint of the internet. Indirectly, that means that I think we should be quite careful about going full on carbon aware everything. Because if you think about it, if all the systems on the planet starts following the wind and the sun blows at the same time at the same location. So we're going to start all trying to go to the same location, which, if you follow the argument, just going to result in a larger peak, which is not necessarily what we want to do. So I'm not saying that we should not do anything carbon aware, but we should be careful about how we do it. So I hope I have convinced you that yes, it is a fact that the internet today is getting emptier, and that is a sustainability problem. But I think that's one problem we can fix.